Hello and welcome to this free preview lecture series of my on-demand FE Electrical and Computer Exam Preparation course. In this lecture, we are going to discuss amplitude modulation. I must warn that there's a lot of math involved in this lecture. In fact, there's a lot of math, specifically trigonometry, in communications altogether. And if you don't have a very comfortable feeling about trigonometry, then you're bound to find communications challenging. So my recommendation is to maybe take a step back and review a little bit of trigonometry before diving into communications. Before we dive into the content, I would really appreciate if you could like this video and click the bell icon and the subscribe button if you haven't already done so. Hello and welcome to part 1 of our multi-part lecture series on the topic of amplitude modulation. Learning objectives of this lecture include introduction to modulation. We will discuss benefits of modulation, why we do modulation, and different types of modulation at a high level. Then we will dive into amplitude modulation. We'll introduce what AM is, and we will look at its time domain representation. Modulation. So what is modulation? Modulation is a process of changing one or more properties of a carrier signal. So these properties can be the amplitude of the carrier signal, the frequency of the carrier signal, the phase of the carrier signal, and so on, in proportion to a message signal m of t. So this is essentially a message signal which will be modulating the carrier signal. This converts the carrier signal into a modulated signal, which is shown as x of t. Demodulation. Demodulation is a reverse process of modulation where you receive a modulated signal and you retrieve the original message m of t from the modulated signal. Now I will introduce a couple of additional terms because they will help us in our discussion of modulation. The first one is baseband signal. Baseband signal is a signal that occupies frequency band from 0 to W. Power is concentrated around DC, that is 0 Hz, and most of the original signals are typically baseband. So in the frequency domain, this is 0 Hz, okay, this is 0 Hz. So a baseband signal will look something like this, okay. So it's mostly concentrated around 0 Hz, and it has a specific frequency band from 0 to omega. And as you can see, most of the power is concentrated around 0 Hz. So this is an example of a baseband signal. Band limited signal. Band limited signal is a signal that has non-zero values only between -W to W, and the total bandwidth is 2W. Okay, so if I were to sketch this on a frequency domain, this is how it would look like. I have W over here and -W over here, and this is a frequency domain, and this is a magnitude in the frequency domain. So you can see that the frequency spectrum only exists between -W and W. The total bandwidth is 2W from here to here, and it is 0 outside of this. Okay, so it is 0 when frequency magnitude is greater than W. So when the frequency in the positive half exceeds W, it becomes 0, and same is true for the negative half. So it is only defined for a very specific frequency range. So why do we perform modulation? What are the advantages of performing modulation? Modulation helps us with transmission. It makes transmission easier because higher frequencies require smaller antennas. The second thing is noise reduction. It limits interferences. When we move the frequencies to a higher range, then we are able to avoid noise, most of which typically exist at a lower frequency range. And then frequency separation. Messages can be broadcasted at different frequencies. Now, let's say you have one radio station broadcasting at this frequency and the other one broadcasting it here and the next one broadcasting here. You can see that it can become quite cluttered. When you can move, if this radio station can move the frequency over here, this radio station can move the frequency over here, and this radio station can broadcast here, then you can see that you avoid that cluttering, and we can use a wider range of frequencies for transmission. Modulation is broadly classified as analog modulation or pulse modulation. Within analog modulation, we have two broad categories: amplitude modulation, which we will start discussing in this lecture and we will carry on in the next couple of lectures. And then we have angle modulation, which we will discuss later on in this lecture series. So in the analog modulation at a very high level, we basically modify the characteristics of the carrier signal, okay? And that can be done by modifying its amplitude, that can be done by modifying its frequency or its phase. Then we have pulse modulation, in which modulating signal, which is your message signal, modifies the characteristics of carrier signal in terms of pulses. We will explore this later on when we start our discussion of PAM and PCM. So in the case of PAM, we have pulse amplitude modulation, where the amplitude of the pulse is changed and it is considered analog, whereas pulse code modulation is PCM, it is digital and it requires us to convert the signal from analog to digital. Amplitude modulation. Let us now formally start our discussion of amplitude modulation. As I explained earlier, amplitude modulation involves modifying the amplitude of the high frequency carrier wave C of t by the message signal M of t. So the amplitude of this carrier wave is modified in direct proportion by the message signal. Let us first take a look at the modulating wave and the carrier wave, and we'll see how amplitude modulation works. So this is a modulating wave. Okay, so it has a positive cycle and a negative cycle, and a positive and a negative cycle. I'm mentioning this because I want to clearly identify where one cycle starts and finishes, right? So this is the start of a cycle and this is the end. Okay, so with the red, this is the end, and the blue basically indicates the start. Now keep an eye on it, because you'll see that the carrier wave actually is of much higher frequency, and the way to notice that or observe it is that in one cycle of the modulating wave, we are able to pack multiple carrier waves, right? So that's why the frequency of the carrier wave is high. Now in this case, we are just sort of showing 5 to 6 carrier waves packed in one cycle of a modulating wave, but in reality, it's not a simple multiple of 5 times or 6 times. It can be 1,000 times higher, 10,000 times higher, or even 100,000 times higher. Okay, so the carrier wave has much higher frequency than the original message signal. So what does the original message signal do? How does it modulate it? So just focus on this carrier wave, okay, and then compare it to the modulated wave. You can see that the modulating wave, which is our message signal, has sort of imposed itself on the carrier wave. So if I were to trace the modulated wave, you can see that it basically makes the shape of the modulating wave, right? So this is the modulating wave, and you can notice that when the amplitude of the modulating wave is higher, then the amplitude of the modulated wave is higher, right? When the amplitude of the modulating wave is low, then the amplitude of the modulated wave is low. And when the amplitude of the modulating wave is lowest, when the message signal is the lowest, then at that time we have the lowest amplitude of the modulated wave. And the frequency of this modulated wave is still the same. So it is still the carrier wave frequency, right? But you can see that it has been modified such that the amplitude is responding to the amplitude of the modulating wave. This was a high-level overview of amplitude modulation, which has other variations. So in this lecture, I will introduce a time domain representation of the amplitude modulation with carrier, or it is simply known as amplitude modulation. And in the next lectures, we are going to look at double sideband suppressed carrier, in which we do not include the carrier, we suppress the carrier, and we actually transmit both upper and lower sidebands as part of the message. And then we have single sideband suppressed carrier, which is known as SSB-SC, in which we either transmit the upper sideband or the lower sideband. You don't have to worry about upper sideband and lower sideband or carrier suppression just yet. We will go through a detailed explanation of all of that, but I just wanted to mention that within amplitude modulation, you have a few different types and variations. And as part of our exam preparation, we are going to look at these 3 different types. Okay, there are a couple of other types, but they're not mentioned in NCEES FE reference handbook, so we won't bother with them. But we won't bother about them. But we are going to look at these 3 different types. Let us now take a look at some of the mechanics of amplitude modulation. How does it really work? So this is a block diagram. We have an information source which is generating the message signal or the modulating signal. To this message signal, we add a DC offset, okay, and I'll explain what this DC offset really means. And then we multiply it with the carrier wave, and that results in the modulated wave. So your message signal is m of t. It will have an amplitude of AM and a frequency of FM, okay? And the carrier signal is C of t. It will have an amplitude of AC and a frequency of FC. And as you know, FC will be much, much higher than FM. And carrier signals are typically sinusoidal. So we can express C of t as a product of its amplitude, A of C, times cosine 2 pi FCT. And you can see over here, FCT is the frequency of the carrier wave. So as we've already discussed, amplitude modulation involves modifying the amplitude of the carrier wave by means of a message or a modulating signal. So right now over here, you can see that C of t is simply equal to AC times this cosine function. So the amplitude is essentially constant, and with time, this cosine function is going to change, and the C of t will basically follow a typical sinusoidal with the maximum amplitude of AC. Okay, and then on the negative half, we will have minus AC. So what I've drawn over here is actually a sine function, but cosine would basically be like this. Okay, so this is AC and this is minus AC. But what we want to do as part of amplitude modulation is to modulate the amplitude. So what we will do is we will essentially embed this m of t as part of the amplitude of CT. Okay, so you can see that we have m of t being multiplied by CT, which will basically modify its amplitude. Now, in this derivation, we are going to assume that this DC offset that I have over here will basically add a DC offset of AC. This DC offset will be equal to, so this plus term is responsible for the DC offset. Okay, this is where I'm adding this DC offset. Okay, and this DC offset is A subscript t, or it is equal to the amplitude of the original C of t. Okay, so that's what it physically means. Now I will show you 2 different derivations. For the first derivation, which is this one, we will assume that our C of t is equal to cosine 2 pi FCT. Okay, and the actual amplitude of this C of t is embedded as part of the DC offset. Okay, I want to explain you how the equation in NCEES FE reference handbook is derived, because it will help you better understand amplitude modulation. And there are 2 ways of looking at that equation. This is the first way, where we basically assume that C of t is equal to 2 pi FCT. All right. Now after that, it is pure math, and we will go about defining 2 new quantities. So what I'm doing in the next step from here to here is I'm basically extracting AC from the bracket. When I extract AC from the bracket, I'm left with 1 over here, and then I divide the message signal by this amplitude AC. And then within the bracket, I will multiply m of t by AM, which is the amplitude of the original message signal, and I will divide it. Okay, so if you multiply and divide it, essentially it doesn't make any difference. And the reason I'm doing that is because I want to bring it to a form which is shown in NCEES FE reference handbook, and then I will rearrange it. I will move AM over here and AC over here. Okay, so that gives me AM divided by AC multiplied by MT divided by AM. Okay, now this is where we are going to define two new parameters or quantities. So the first one is modulation index, which is defined as the ratio of the amplitude of the message or the modulating signal to the amplitude of the carrier signal. Okay, so AM divided by AC, this is the modulation index. Then we have the normalized message, which is nothing but the message divided by its maximum amplitude, okay, or its amplitude or the maximum value. Okay, so this is the normalized message. Now I can substitute it back in the equations. So I replace AM by AC with A and MT by the amplitude of MT with the normalized message. And now you can see that your time domain representation of the amplitude modulated wave looks very similar or identical to the equation that is provided in NCEES reference handbook. Over here though, one key thing to notice is that I actually have AC. I don't have AC dash, and I will explain this as part of the next derivation of the same equation. But the key takeaway over here is that we are modifying the amplitude of the carrier wave, okay? And that can be represented by this equation. It is a function of the modulation index and the amplitude of the carrier wave, as well as the message which is embedded as part of this modification of its amplitude, okay? Now this is a second derivation of the same equation, and I'm going through this exercise because there's a little bit of ambiguity with respect to the notation of the equation that is given in NCEES reference handbook, but this is another take at it. So what we are going to do, again, we will start with the same basic equation, which basically says that the amplitude of the carrier wave is being modified. Okay, this is amplitude modulation. So I have AC plus M of t. Again, this DC offset is going to be AC. So I'm adding AC, okay, to M of t, which is our information source, the message signal or the modulating signal. Now you can notice over here, I have defined C of t as AC times cosine 2 pi FCT, just like how we defined it in its original definition. We said that, okay, C of t will have an amplitude of AC and it will have a frequency of FCT, and it is a cosine function, okay? And in the next step, I'm basically repeating the same process. I extracted AC out of this bracket. That basically gives me AC times AC. Okay, so you already have one AC. When you extract this AC out, then you will end up with AC square. Okay, and within the bracket, you have 1 plus MT divided by AC, and then you are left with the cosine over here. Now you can see that this is no longer AC, all right, and this is AC square. So that's why in NCEES reference handbook, potentially, they have identified it as AC dash. Okay, so it's like a new AC or a modified version of the original AC. So this is what we are going to carry in the equation moving forward, and the remaining steps are basically the same. You multiply and divide by the amplitude of the message signal, you rearrange it, you group this together and you group this together, you define modulation index as AM divided by AC, you substitute it back here, you define normalized message as MT divided by AM, and you substitute it here. And you can see that you basically arrive at a very, very similar equation that we derived previously. The only catch here is that we are saying that AC dash is not really the same AC which we started out with. It is a modified AC. Whereas in the previous equation, by setting C of t equal to cosine 2 pi FCT and simply adding AC to M of t, we were able to keep the AC same. Okay, we were able to keep AC the same value as the DC offset value. But over here, the AC that we end up with in terms of the AM is actually AC square, and that's why in NCEES reference handbook, it is identified as A-C. In this lecture, we introduced modulation. We looked at its benefit, why we do modulation, and different types of modulation. And then we dived into amplitude modulation. We looked at it at a very high level and graphically saw how the message signal can modulate the amplitude of a carrier signal. And then we started deriving its time domain representation. For further practice, I'd recommend you to check out the quiz at the end of the lecture and also consider problem sets in the study guide and practice exams. Thank you. If you found this preview lecture helpful, I am confident that you will also greatly benefit from the full course that contains over 150 lectures and covers all the topics that are found in the latest NCEES FE Electrical and Computer Exam specification. You will also get access to tons of quizzes and mini exams in this course that will help you get additional practice, along with a bonus full-length computer simulated practice exam. This streamlined and well-reviewed course comes with an amazing 30-day full refund policy, no questions asked. On top of all this, I have also included a special discount link in the text section of this video.